Hi all, I am James Mathew, Assistant Professor, Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. Today I am going to discuss about the topic transient or unsteady state heat conduction. This is one of the topic in the third module of the course Heat and Mass Transfer. In the first module of this course, we have discussed basically the steady state heat conduction with and without heat generation, and in the second module, the convection heat transfer. As we all know, if the temperature of a body does not vary with time during a heat transfer process, it is called a steady state process. That means the temperature is a function of space coordinates only. Now consider a more general situation in which a body experiences an abrupt change in its surface temperature. For example, heat treatment of metals by quenching. The body attains an equilibrium temperature after some period. So during this period, the temperature varies with time and the body is said to be in unsteady or transient state. In general, we can say the temperature is a function of space coordinates and also time. This change in temperature may follow periodic or non-periodic variation. If the temperature at any point within the system varies non-linearly with time, then it is called non-periodic variation. Examples: cooling of bars and metal billets in steel work. In periodic variation, the temperature undergo periodic changes which are either regular or irregular but definitely cyclic. Examples are, we consider a building during a period of 24 hours. During daytime, the building will heat it up, and during the night time, the building will be cooled. Now, a major simplification is obtained here by assuming the temperature variations within the body are negligible. Suppose the body has a very high thermal conductivity. Obviously, the temperature variations within that body is always going to be very small, and its internal resistance can be assumed negligible in comparison with convective resistance at the sun. So the temperature of such bodies can be taken to be a function of time only. So heat transfer analysis that utilizes this idealization is known as lumped system analysis. Now let us derive the differential equation for this situation, that is the bodies with the negligible internal temperature gradients. So that consider a body having volume V and surface area AS. It could have any shape. Let the initial temperature of the body be Ti. Now consider the situation that this body is placed suddenly in ambient air or any other fluid at a temperature Ta and heat transfer coefficient H. So this body during the unsteady state loses or gain heat from the surrounding fluid. If Ti is greater than Ta, then the body is going to cool. If Ti is less than Ta, the body is going to heat. If we neglect internal temperature gradient, the temperature will only be a function of time. So we would like to find how does the temperature vary with time for such situations. Let's formulate the problem now. If I apply the first law of thermodynamics to the solid body at any instant of time during the unsteady state cooling process, we will get a rate of change of energy of the solid body, that is rho v Cp dt by dt. Rho v, one second, rho v is the mass of the body, Cp is the specific heat, dt by dt is the rate of change of temperature with respect to time. This must be equal to the rate at which the heat is transferred from the body to the surroundings, that is HAS T minus TA, where T is the temperature of the body at any instant of time in degrees Celsius, TA is the ambient temperature, and tau is the time in seconds. Here we have two variables. The temperature is varying with respect to time. So let's rearrange the equation and apply the integration. We will get minus HAS rho VCP, all are constants, into integral d tau, that is the variation of time, that is equal to integral dt by t minus ta. So we will get ln of t minus ta equal to minus HAS tau by rho VCP plus the constant of integration. Let's put this equation as equation number 1. In the previous slide, the negative sign in the equation indicate the direction of heat flow. If the body is cooling, then the sign will be negative, and if it is positive, if it is heating, then the sign is positive. Now, to find the constant of integration, apply the boundary condition. That is, at the time tau equal to 0, the temperature T of the body is equal to Ti. So if we apply this boundary condition, we will get the constant of integration C1 equal to ln of Ti minus Ta. Now substitute the value of C1 in the equation number 1 and rearrange the equation. We will get ln of T minus Ta divided by Ta minus Ta equal to minus HAS tau by rho VCP, or in the form dimensionless temperature term equal to exponential of T minus Ta divided by Ta minus Ta equal to exponential of minus HAS tau by rho VCP. This equation indicate that the temperature variation in a lumped capacitance body is exponential. that is shown in this diagram, T versus tau time. Now the term rho VCP by HAS, is called time constant, which is denoted with tau star, and this quantity indicate the rate of response of a system to a sudden change in the environment. Though this we will see detail in the next slides. Also, this term tau star we can write like this: 1 by HAS multiplied with rho VCP, where 1 by HAS is the thermal resistance, convective resistance at the surface, and rho VCP, that is MCP, is the thermal storage capacity or the thermal capacitance of the body. Now, if you would like to find the heat flow rate at any instant of time during the process, you can use the equation, the instantaneous heat flow Qi equal to minus rho VCP dt by dt. From the temperature distribution equation, we will get dt by dt equal to Ti minus Ta multiplied with exponential of minus HAS tau by rho VCP into minus HAS by rho VCP. Now substitute the value of dt by dt in this equation and rearrange. You will get the instantaneous heat flow rate equation Qi equal to Ti minus Ta HAS into exponential of minus HAS tau by rho VCP. You can also use another equation to find the instantaneous heat flow rate, that is equal to HAS into T minus T infinity minus TA, T minus TA. TA is the atmospheric temperature. T is the temperature at the time tau. Now, to find the total heat flow rate during a time tau, we can integrate this instantaneous equation at the limit 0 to tau. That is, the total heat flow rate during some time interval Q equal to integral 0 to tau Ti minus Ta HAS e raised to minus HAS tau by rho VCP dt. So you will get Q is equal to rho VC Ta minus Ti, to make this quantity positive, Ta minus Ti e raised to minus HAS tau by rho Vc minus 1 bracket. Or you can use another equation, which is Q is equal to rho VCP, that is MCP, multiplied with the temperature change in the body, that is T minus TO, T minus Ti minus Ti, which is the initial temperature of the body. T is the temperature of the body at that instant during time tau. Now, the exponential term HIS tau by rho VCP can be expressed into two dimensionless numbers, Biot number and Fourier number. For that, multiply and divide this term with KAS into V and rearrange, we will get H by K into V by AS into K tau by rho Cp V by AS the whole square, where V by AS is called the characteristic or equivalent length of the body, which is denoted with LC, and we also know K by rho Cp is the thermal diffusivity alpha. So you will represent the equation HIS tau by rho VCP equal to HLC by K multiplied with alpha tau by LC square, where HLC by K is a dimensionless number which is called Biot number, and alpha tau by LC square is the another dimensionless number called Fourier number. You might have remembered the equation for Nusselt number, which we discussed in the convection problems. You have the same equation HLC by K for the Nusselt number also. But the main difference between the Nusselt number and the Biot number equation is, in case of Biot number, the K, the thermal conductivity, is the thermal conductivity of the body. But in case of Nusselt number, the K denotes the thermal conductivity of the fluid which is flowing over the solid. Now, the dimensionless temperature term T minus TA divided by Ti minus TA will be equal to exponential of minus Biot number into Fourier number. So it is evident that from the equation of Biot number, if the thermal conductivity of the body is large, which is our major simplification at the beginning, then the Biot number is a minimum value. So the lumped system analysis is applicable only if the Biot number is less than or equal to 0.1. The Biot number we can represent like this. It is the ratio of convection at the surface of the body to the conduction within the body, or in other words, it is the ratio of conduction resistance within the body to the convection resistance at the surface of the body. Now let us discuss one major application of lumped heat capacity method, that is the temperature measuring instruments. We already know the temperature distribution in this situation, T minus TA divided by TA minus TA equal to the exponential of minus HIS tau by rho VCP. The response of a thermocouple is defined as the time required for the thermocouple to attain the source temperature. It is evident from the above this equation that the larger the quantity minus HIS by rho VCP, the faster the exponent time will approach 0, or the more rapid will be the response of the temperature measuring device. That is, more rapidly the temperature T will approach the TA. So this can be accomplished either by increasing the value of H or by decreasing the wire diameter, density and specific heat. This is the reason why we use very thin wires in thermocouples or temperature measuring instruments to ensure a rapid response. We know time constant tau star. This term we have come across one of the previous slide. Tau star equal to rho VCP by HIS. So we can rewrite the temperature distribution equation as e raised to minus tau by tau star. When this time tau equal to tau star, the temperature term, the dimensionless temperature term T minus TA divided by TA minus TA will be equal to e raised to minus 1. That is equal to 0.368. Thus, tau star is the time required for the temperature change to reach 36.8% of its final value in response to a change in temperature. In other words, tau star is the time required for the initial temperature difference would be reduced by 63.2%. The time required by a thermocouple to reach its 63.2% of the value of initial temperature difference is called its sensitivity. Now, the diagram shown here indicates the variation of dimensionless temperature term with respect to time for different values of time constant tau star. Time constant tau star. So it is evident from the curves, each curve, that if the time constant tau star is less, the more rapidly the thermocouple or the temperature measuring instruments will respond. So all the above equations we come across in the different slides, you can find from the Heat and Mass Transfer data book by C.P. Kodandaraman, 9th edition, from page number 66. Now, let us discuss two simple problems in this topic. The first problem: a 10 centimeter diameter apple, which is approximately in spherical shape, is taken from a 20 degrees Celsius atmosphere and placed in a refrigerator where the temperature is 5 degrees Celsius and the heat transfer coefficient H is equal to 6 watt per meter square Kelvin. Calculate the temperature at the center of apple after 1 hour. The thermophysical properties for the apple are rho equal to 998 kilogram per meter cube, specific heat of the apple is equal to 4180 joule per kilogram Kelvin, and thermal conductivity of the apple is equal to 0.99 watt per meter Kelvin. So before going to apply the equations, we should first check the validity of lumped system analysis. For that, we should find the Biot number, which should be less than or equal to 0.1. So to find the Biot number, you have the equation HLC by K, where LC is V by AS. For spherical body, surface area equation is 4 pi r square. So you'll get the surface area as 0.0314 meter square, and the volume for the spherical sphere is 4 by 3 pi r cube. If you substitute the values, you will get which is 5.23 Newton raised to minus 4 meter cube. So substitute the value for here, you will get the Biot number as 0.1. So this is applicable, this problem is applicable for the analysis of lumped system problems. Okay, so here we want to find out the temperature of the apple after 1 hour. So the given values are, the diameter of the apple is given, initial temperature of the body is given, that is 20 degrees Celsius, which is placed in the atmosphere, which is at a temperature of 5 degrees Celsius, it is also given, and the heat transfer coefficient is given, and the time is 1 hour, that is that is 3600 seconds. So this is your temperature distribution equation for a lumped system analysis. T minus Ta divided by Ta minus Ta is equal to e raised to minus His tau by rho Vc, where the only unknown parameter is the temperature. So substitute all the values here, you will get the time T is equal to, calculate the time, the temperature T equal to 15.99 degree Celsius. Now we will discuss another problem. A 6 centimeter diameter potato, which is also approximated as a spherical body, at initially at 20 degrees Celsius, is suddenly dropped into boiling water at 100 degrees Celsius. The heat transfer coefficient H is equal to 6.5 watt per meter square degree Celsius. Take alpha equal to 1.6 into 10 raised to minus 7 meter square per second, which is the thermal diffusivity, and the thermal conductivity equal to 0.68 watt per meter square watts per meter degree Celsius. Determine the time required for the center temperature of the potato to reach 95 degrees Celsius and the energy transferred to the potato during this time. Okay, so here also for the validity of lumped parameter analysis, check the Biot number, which is HLC by K. You will get 6.5 into 0.03 by 3, that is the characteristic length of the sphere, r by 3. Okay, 0.03 is the radius of the sphere, so r by 3 is the LC value. So you will get number as 0.096, which is less than 0.1. So this problem is applicable for the analysis, lumped parameter analysis. Okay, so these are the given values. To find the time required to reach the body from 20 degrees Celsius to 95 degrees Celsius, we have the equation T minus Ti divided by Ta minus Ta equal to e raised to minus Pi into Fo. We use this equation because in this problem it is not given the values rho of the body and Cp value of the body. So instead of that, they have given the alpha value, the thermal diffusivity value. So the only unknown in this equation is the Fourier number. So you can find out the Fourier number by substituting all other values. You will get the value of Fourier number is 28.88, and we know the equation for Fourier number, which is alpha tau by LC square, where LC and alpha is a non-quantity. So you will get the time tau, which will be 5.01 hours. Okay. Now the other question is to find the energy transferred, total energy transferred during this time 5.01 hours from the body. So to find the total heat transferred, you can either use this equation which we have derived earlier, or you can use the simplified equation, this equation, which you can find from the data book, page number 66. Okay, here instead of for this rho VCP, instead of rho VCP, you can use this equation HIS tau by Biot number into Fourier number, which we have already derived. HIS tau by rho VCP we have represented as the product of Biot number and Fourier number earlier. So you can use, instead of rho VCP, you can use HIS tau by Biot number into Fourier number here, and you will get, if you use both the equations, you will get the same answer, 35.89 kilowatt. Thank you.